Hello, I'm Martin Reyes, and today I'm going to be talking to you about estimating quantitative data from qualitative results obtained by ultrastructural retinal staining through image processing in MATLAB. That's kind of a mouthful of a title, but we're going to go ahead and walk through this presentation and talk about this code that I developed. So first of all, problem. So there's two different types of data. I don't have to explain to you. But we have qualitative data, right? That's going to be essentially data that has no numbers or analytical information. That's just going to be observations, right? So we have candles here. Maybe we're observing a candle over time as it melts. We're not really taking any measurements. We just have a picture that shows us over time it melted further and further and got smaller. As opposed to quantitative data, which is going to be highly number-based, right? And maybe we're modeling the rate of decay of these candles over time, or some sort of numerical property of these candles, right? That's going to be our quantitative data, and oftentimes more than anything, this quantitative data is going to be very good for making bold conclusions and results to whatever set of data you report. So now there are some times that we're going to use qualitative data, right? So sometimes maybe it's just easier to show a picture. If it's not a very important thing and you just kind of need to convey the idea, just show a picture and that'll get the take-home method through. So sometimes maybe a method they used did not compute quantitative values, right? Maybe you don't have access to the data for what you're looking at, and maybe it's just difficult to quantize those results. So this bears a question. If we can visually evaluate these differences in an image, can't a computer too? And definitely can. A whole field of it called image processing, right? And this is going to be using computers and to evaluate and create conclusions from images. Maybe you're assembling an image based on data points, but you can do a lot of things, right? Using inherent properties of images such as luminescence or color values, right? So in the MATLAB script that we're going to be looking at today, we want to go ahead and achieve a few things here. And so first, I want to go ahead and allow the user to upload images of figures that they want to evaluate. And let's say that maybe there's some text or some borders that are there. Let's try to have the script remove them. And then lastly, we're going to utilize image processing methods to create quantitative comparisons, right? Where we're actually getting numbers, differences between these images. So we're going to have to make some assumptions, though, in order to achieve this. So first of all, we're going to say that figures have to come in pairs. So we're going to have a control figure, and then we're going to have an experimental data figure, right? So one figure, and then another figure, and we're comparing those two. Now, the differences in figures should be observable, not inferred. This is kind of explanatory in that you need to actually see the image. The computer actually needs to see that difference in those two images. And there's going to be a lot of tinkering. A lot of tinkering around we're going to have to do to try to get these methods to work properly. So let's go ahead and look at some key concepts here that we're going to have in our script. First of all, binarization. And what that's going to be is you take an image, preferably a grayscale image, and the computer runs through this true and false analysis of this image, right? Using a specific threshold, and it's going to detect instances that it determines are true. This is going to be based on luminescence here, right? So we see here that maybe white is true, black is false, vice versa. But that's going to be a good way of segmenting key parts of an image. And we're going to use that a lot in our code. And next up, we have k-mean clustering. And without getting too technical about the whole process, essentially we're going to be separating dominant colors in what are called clusters. And so we're going to be using three. We're going to be using three for our clusters, and we're going to develop 3 clusters in our code to kind of separate those colors out. And then next up, we have 2 different color spaces. So RGB color spaces, standard red, green, blue. A lot of people are very familiar with this. If you work with photo photo programs such as Photoshop or whatnot, that sort of editing software, you'll be quite acquainted with this. And then lastly, we're just going to abbreviate as LAB, color space, right? And this is a three-dimensional plotting of properties of color in an image. So we're going to have this luminescence as our vertical axis, and then we're going to have our two axes here that represent four significant colors in our color set perception. So I've created two methods that we're going to be using for our image processing. The first is going to be an automatic method, and it's going to require no user input, right? It just takes the images. It will segment the images into three composite layers, so your red, your green, and your blue layer. And then it's going to determine which of these RGB layers is the most dominant in the image. And it's actually going to do this by calculating the mean of luminescent values. And based on whichever red, green, or blue layer had the highest luminescent, it will determine that that is the color that dominates. So it's going to separate that layer out, and then it's going to create the summarized image and binarize that to compare pixel expression. And this is a unitless idea. This is a unitless term, and it's just saying that how, like for instance in this image, how much of the rice is shown, right? How much of these values are true. That's what we'd consider pixel expression, just the prevalence of data that it picks up. And then lastly, we're going to have this manual method, and it's named that because the user is actually going to have to work with the program here. So it's going to perform k-mean clustering, and it's going to segment. We used lab as our color space. It's going to segment the image into three clusters, right? So then it's going to actually ask the user which cluster of information best represents the data that they're interested in. And this will make a lot more sense when we actually run through the code together. And then lastly here, it's going to binarize that clustered image and compare the pixel expression, right? So just the prevalence of the color that it's looking at, kind of like it did in the automatic method. But we're going to see that even though these two have some similarities, they come to very different conclusions in our code. So all of this code would be useless if we didn't actually apply it to something. So we're going to be looking at a test case here, and this is actually from an article that I had the pleasure of reading. It came from the Department of Ophthalmology at West Virginia University, and it is about the loss of mitochondrial pyruvate channels in how it affected retinal metabolism and eventually led to impaired vision. So this whole experiment was done using what are electroretinograms, and that's going to be analyzing the eyes, the retina of mice, and it can determine the health of the retina, photoreceptor responsiveness, bipolar cell responsiveness. And so again, here's the MPC channel that we're going to be looking at. It is a very important channel in facilitating this transfer of pyruvate into the mitochondria, which, as you'll remember, is a very important product to start the TCA cycle, and that whole metabolism process relies on it. So we're not going to be talking too much about the metabolism parts of their results in this paper, but what we are going to be looking at are the structural defects that photoreceptors undergo through this MPC deprivation, right? So here's a standard rod, and we have highlighted here the outer segment of the rod, and this is going to be an important segment, outer segment, inner segment, and we're actually going to see this part of the structure of the photoreceptors get shorter and decay off, and this is going to greatly impair visual acuity. So here are two significant figures from this part of the report. So we see here in figure 2, and we can just boom these up, what we're going to be analyzing. We can see here postnatal day 20 when they analyze this. MPC is going to be, the MPC knockout, our experimental method, is going to be this red here. And we can see that there's a little bit of a difference in outer segment length, right? The photoreceptors are a little bit shorter than they should be. The qualitative data, it's not as noticeable, but when we go to postnatal day 30, postnatal day 90, right, as time increases, we significantly see that these outer segments of the photoreceptors are getting smaller, and this is indicative of that retina degeneration. And we can actually, now we can see qualitatively, it is having an effect on the retina. The retina is getting smaller, right? It's degenerating. And so we're going to be looking at this data here. Now here, they actually gave us some quantitative results, right? But if you notice here in figure 3, as far as I could see from the report, this is what we're given. These are biofluorescent stains, right? We have sodium, potassium, ATPase, rhodopsin, the combination of the two in DAPI to indicate parts of the retina here. And our main interest is going to be that between the outer segment and the inner segment of the retina, right where the photoreceptors are located, we're going to see this unique ultrastructural feature to where it's degrading. We have this gap here between this junction, and that's going to further give rise to this idea that the retina is degenerating, the photoreceptors are dying off. So we have a few questions that we want to ask as we run our code. First of all, can we use image processing to identify differences in our subfigures? And second of all, what advantages and disadvantages are prevalent in each method, right? The automatic and the manual method. And then we're going to conclude which method is better for the image processing, just overall. And then lastly, using figure 2 that we saw that where they gave us the quantitative data as well as the qualitative data, we're going to verify the integrity of the best method that we choose. So this point onwards, I'm going to go ahead and walk through the script with you. Alright, so starting off here, we have our file directory, and this is the main file. This is the main folder where you're going to have the script that you want to run. Here's a folder right here called Put Figures in here, and you can go ahead and see here that I've spliced up manually. I did this in a PowerPoint actually. I spliced out figure 2, the parts that we want to analyze, right? So we have our control and we have our knockout experimental data, and then I spliced up figure 3, the parts that we want to see. And they're not perfect, right? They have a little bit of borders, they still have the text on them, but hopefully the code is going to take care of that problem, at least enough to not affect results. So let's run AVR run me, and we're going to wait for MATLAB to boot up here. There it is. So right, you just want to execute this. And here we go. So we start off with our first main menu option, exit program, but we're going to go ahead and do image analysis instead. Let's open that up. So it's asking us if we'd like to import or continue from where we left off. We haven't imported any data yet, so let's go ahead and do that. So it actually pulled up in my other monitor, but it's asking us how many subfigures do we have in total. So we actually have 6 subfigures, right? Let's go ahead and start off with figure 3. It doesn't really matter which one you start off with. I just want to go ahead and start off with figure 3. So file name of control subfigure 1. We're going to go ahead and start with this one here. That is the control figure. Then it's asking us, if you saw there, file name of experimental figure subfigure 1. And remember, so this is our control. This is going to be our experimental one, the knockout. So control subfigure 2. And you kind of get a pattern here. Experimental subfigure 2. It's that one. Control subfigure 3. It's this one. And then experimental subfigure 3. It's going to be this one. And you can put any number of subfigures, right? You could do 4 in total, 7 in total if you wanted to. But we just have three pairs. So does this look correct? I think about it looks correct. If it didn't, you could retry that process, but we're going to go ahead and say yes. Now it asks us the next step, right? If our figures contain any text, and it does. It contains white text, so we're going to say yes. Now at the moment, it can only decipher between white and black text. I don't know why you'd have other colors, but we're going to go ahead and say that we did have white text. And it does a fairly good job of trying to eliminate that. It's not perfect, right? Ideally, you'd want to have this be covered up with blue, but for the time being and for the processes, it's not going to matter too much. So it seems to have done well. We'll go ahead and continue with this for right now. Now it's going to ask us if you would like to process the images automatically or manually. And these are the two different methods that we were talking about earlier. So let's start with automatic, right? Kind of the one that deals with RGB and separating them based on whichever color is expressed more. And we can actually see here, so it printed out some stuff in the command window down here. But just looking at our figures, we can see that this first set, it seems to have binarized them quite all right. And there's not much of a difference, right? 7.59 is not too big of a difference, but enough that it still calculated it. We see this in the graph here that graphs pixel expression. So our control here, kind of toe-to-toe. But in figure 2, we see this a little bit, right? 14.8%. There is quite a difference between those. And this was easy because this one was just stained in green. This one was just stained in red. So it was able to find that those colors easily. But where it falls apart is whenever you have multiple colors in a figure. And so here it didn't know which one it wanted to prioritize. So we end up seeing this 47% difference. And we know that's not the case. That's too wild and too extreme. And we understand why it didn't perfectly compile this one. So this is where the manual method comes in. And we're going to go ahead and see how it plays out. So here are the clusters, right, that we did from the k-mean evaluation. And we see here that for our first control figure, it looks like it did cluster 2 seems to be the biofluorescence that we're looking for in the sodium potassium ATPase expression. So we're going to go ahead and say cluster 2, right here. That's the one that best represented our data. Now we have our other control figure. So it's going through the control figures first. And cluster 2, again, seems to be representative of what we want. So let's just go with cluster 2 for right now. Next up, here's an interesting case, right? Because we have 3 different colors that dominate in this image. And so the 3 clusters, we kind of like to analyze all of them at the same time, right? Not just choose one over the other. So we're going to select on this option here, multiple clusters. And it's going to give us options 1 and 2, 1 and 3, 2 and 3. But we're going to say all of them. We want to analyze all of them. So let's go with clusters 1 through 3. So it's plotting them in the background there. It's assembling that plot. And now we're going to go through our experimentals. So we have the experimental figure. So cluster 1 seems to do a pretty good job there. Let's go with that one. Experimental subfigure. Cluster 3 seems to get the idea across, so we're going to go with that one. And then next up again, here we go. With this last one, we're going to choose all three clusters. So now we have our final figure here, kind of the complete results to compare against the automatic method. And this green and magenta here, don't worry, it is computing the binarized data. This is just a product of the way that I compiled the images and the clusters. So, but it doesn't make much of a difference. It's cosmetic. So now we see down here, we get different percent values, right? On our first column one, when we did it automatically, we got 7.59. Now we're actually getting 9.38. And we can kind of tell it did a very good job of highlighting the important data. And we can see that these 2 images are relatively close to one another. Now, surprisingly, we actually get a major percent difference here in the figure 2 part. And if you do think about it, right, this image in that where we're seeing that the photoreceptor defects between the outer segment and the inner segment, it actually does make a pretty big damper on the data that we're evaluating here. So it does make sense why this value has gone up exceptionally, especially since it really is just focusing on this stained area. And then lastly, we see that it does compute a fairly reasonable difference between these 2 images. We get a 27.27%. And, you know, unfortunately, some of that text still is appearing. But hopefully we can develop a better method in the future of tackling that. So now we've seen the automatic and manual compared side by side with that figure 3 from the report. And let's go ahead and go back. We're going to import some new data because we also want to look at that figure 2, right, the H&E staining figure. But for right now, I think we should go ahead and move forth with the manual option, because it does a very good job of tackling multiple colors that aren't just red, green, and blue. So let's close these figures. And now last thing we're going to look at here is we're going to import some more data. And this is going to be the same drill as earlier, right? You could put in however many, but we're doing 6. So just go ahead and upload control experimental, control experimental. Luckily, these are laid out pretty nicely. So we're going to go ahead and nab this last one here. Now, if you made a mistake, oops, it's all right. You can always try again, but it looks good for what we're doing. Do the subfigures contain text on the image? Yes, again, they do. But this time, the text is going to be black. Now, you're going to notice initially it doesn't really... It identifies some parts of it, and it's trying to erase it. But the threshold is a little too low initially. And I demonstrate this because you can actually try it again and determine your own threshold that you'd like to try. So right now it is set to black, and this is from a scale of 0 to 255, going from the blackest to whitest. And so since we're trying to filter out the black text here, let's go ahead and knob this up to, let's do 20. You could try any set of numbers, and if it had made undesirable results, you could try it again. But for the sake of this demonstration, this is fine. So we're going to go ahead and just continue with that. I don't want to be staying here tinkering forever. So again, we set that for the more complicated structures, we're going to go with manual. So we see here cluster 1 and cluster 3 seem to be representative of the data we're looking at. So let's go ahead and choose those 2 clusters, right? 1 and 3. Next up, cluster 2 and cluster 3 seem to be pretty good. So let's go ahead and do 2 and 3. Once again, 1 and 3 seem to be the best ones. So this should finish off our control figures. Now we're going to be doing our experimental figures. 1 and 2. Let's go with those. I like those. Let's see here. 1 and 2 again. Not very exciting this is, but you know, this is an important part of this process. 1 and 3. Alright, so here we go. We have plotted our figure here. And again, remember the green and magenta, don't worry too much about them. The calculations are what matters, and it's calculated them pretty all right behind the scenes. And so what we see here is that in this set of figures, right, we get a percent difference of about 7.75. So these figures are 7.75% different from one another. And that makes sense, right? Because at postnatal day 20, they had made the resolution that nothing too drastic had changed as far as the degeneration of the retina had gone. So we're not getting anything that extreme, but once we get to postnatal day 30 right here, we can actually see that this has gone up significantly in the difference between these 2 images. And even though we have some impurities like what's going on up here and a little bit of text coming out, for the most part it actually does align with our data in that. And look, as we go to postnatal day 90, you see we are actually getting differences in these images because the experimental images, their retinas are degrading, right? The overall structure of the retina is getting smaller and smaller. Those outer segment layers of the photoreceptors, they're getting smaller and smaller too because they're decaying. So this does match up with what they had quantitatively and qualitatively provided in their report. So this is the extent of the script. We could always tinker and mess around with different settings, but we're just going to go ahead and go back to the menu and resolve our PowerPoint. So exit program. Alright, so now that we have finished up looking at the code, let's go ahead and refer back to the questions that we had talked about earlier, the four here. So first of all, can we use image processing to identify differences in our subfigures? And I'm going to give that an emphatic yes, but we still have to give our consideration to our earlier assumptions that we made, right? So I'm going to go ahead and go to number 2 here. What advantages and disadvantages are prevalent in each method? And we saw that in the automatic method. It did a pretty good job of whenever the biofluorescent staining had one color that it was looking at. And it binarized them quite alright. But where it fell apart was when we had a figure that had multiple different colors of biofluorescent staining. And we couldn't use it for that because it was just trying to find one predominant color. So it did a pretty good job with these, but it wasn't very good for our control figure, our set here. Now the manual option, well, you know, not perfect, right? Neither of these are perfect by any means, but they do a pretty good job of getting some answers out. The manual seemed to have fared better overall, I'd say. Even so much so that it really analyzed the data that we got here from this staining. I believe it was the rhodopsin staining, and it did say that this ultrastructural defect here is significant enough to impact our results, and we got a fairly big difference there. And even for our last set of figures, right, we're analyzing the different colors, it was able to show that there is a difference between these figures, and that is because of that ultrastructural decay that we observe here. That is taking an impact, and the retina overall is decaying, and the knockout are experimental results. So now we ask which method is better for image processing overall, and I'd say that the manual approach that we looked at was probably the best, just because it had that big advantage with this set of figures right here. And even just minor minor fluctuations in color, if they're not specifically RGB, it's going to do a better job with that because it's working on that lab color space. So last question here, can we verify the integrity of the best method? And that was the whole reason of looking at figure 2 here. And I'd say we can verify the integrity of this script here, because when we had our quantitative results, it matched up in showing that, hey, the MPC knockout, right, these outer segment layers are decreasing, are getting significantly smaller as time progresses for the knockout mice, right? And we see that qualitatively here with the retina getting smaller and smaller. And when we evaluated that in the code, we did see that on especially these two experimental figures, there was a big difference in comparing them with the control figures. And so as we see, right, postnatal day 20, postnatal day 30, postnatal day 90, over time, we do see this difference in the image, which is indicative of that degeneration of the retina of smaller and shorter outer segments in the photoreceptors. So I'd say that does a pretty good job of validating the integrity. So just here, summarization of our answers that we've looked at. So nothing is perfect, and of course there's always going to be future improvements, things that could be refined on, and this script is no exception, right? So uploading the data, overall I think the process is pretty smooth and I'm happy with how it came out. An earlier iteration had a much more archaic version of this where you actually had to type in the file name, but luckily enough I think it's pretty okay, but maybe it'd be good if we allowed for multiple image uploads instead of one by one. Now for the text removal part, there's many things that could be improved. It gets the job done, but we could definitely develop a more efficient method for replacing the text with that background color. Like when we were looking at the DAPI stain, right, that was blue, I had mentioned that it'd be better if we filled in instead of that black color for the text, if it could just mock that blue color that we were looking at. So just further tinkering with the thresholds for text detection. The automatic method could definitely use some improvements. It strives and it does pretty well with single color biofluorescent images, but again, we can maybe design an alternative method for more than one important color. Just kind of further tinker around with those thresholds for what is considered the dominant RGB layer. And then, again, just make it so that way it's not so dependent on red, green, and blue colors, which is why we ended up going with a different color spectrum color for the manual method. But anyways, lastly here, the manual method, right? I'm pretty happy with how it turned out, and I think it does a very good job. But you know, we could allow the user to further tinker around with some thresholds. So you saw that k-mean cluster, it was only set to give out 3 clusters, but maybe a future iteration of this code could let the user choose to that degree how many clusters does it want to analyze. And so there's a correlation between the amount of clusters and the noticeable colors that you see in an image. So that would be something that'd be great, because if you had 6 biofluorescent stains in a single figure, maybe you'd want to go with 6 clusters. Further tinker around with the user interface, that could always be an improvement. And then lastly, this is more of a cosmetic thing. When it displayed those figures that were green and magenta, maybe have it display either the original figure or the binarized true or false black and white figures. It didn't impact the actual calculations themselves, but it would make more sense for the user who didn't expect or maybe got confused as to why those colors showed up, even though it didn't have much of an effect on anything. So that's about it for this presentation. I'd like to have some folks here to thank, of course, the wonderful people at the West Virginia Department of Ophthalmology, whose research and figures I used for my test case. And I'd like to thank my professor, Dr. Nash, the University of Houston, Department of Biomedical Engineering, and of course the viewer, you, for going through and getting through this lengthy video. So that's about it. Thank you.